last time we were talking about PCB antennas. This time we are going to talk about chip antennas. And Katerina is going to help us to understand this topic. She is designing antennas, so she's the right person. Is it right? That's what we are going to talk about, chip antennas.
Yes, yes. Hello, everybody. I'm Katerina Galitskaya, senior antenna engineer. I have 10 years experience in design antennas for consumer electronics, wearable devices, cellular devices, base station antennas, and so. So today, as Robert said, we would talk about chip antennas, how to place them correctly, how to choose, how to ensure proper efficiency of your antenna, and what you need to take into account.
When we would like to use chip antenna and what chip antenna actually is.
Yeah, well, chip antenna is basically a PCB antenna that is not printed on PCB, but is a kind of block of the shelf antenna, so-called, that you buy from like ready-made already from some vendor, and then you can place it into your device. So it's in a sense, it's ready-made solution that you buy, and it can be convenient sometimes, but you also lose a bit of flexibility maybe with that, because you cannot change it anymore. Maybe you can tune it a bit within matching network, but cannot change it anymore with like the design itself of the antenna. So here, for example, we have Molex chip antenna that's 4G LTE antenna, dual band that works 700, 960 megahertz, and second band is 1.7, 2.7 gigahertz. We have this antenna in simulation, like the box of the antenna in simulation, and the reference board that they recommend in datasheet. And here comes the first very, very important thing about chip antennas, that chip antenna only performs according to datasheet when placed on a reference board that is specified in datasheet, and also when placed exactly as it's specified on datasheet. So any alteration that you do will affect the efficiency and the performance of your antenna.
Okay, I would like to interrupt you here. So it basically means when someone buys chip antenna and place it on the board, and they will be like, oh, I place antenna on my board. It's not like it's not so simple. It's not like connecting the external big antennas. Even
yes, exactly.
Okay.
Exactly. You're completely right. That's why I always really want to warn people about cheap antennas, especially those who are maybe a bit far from antennas, just some engineers, maybe some amateurs who want to just have some antenna in their device, and they think that cheap antennas is very good, right? You can buy already antenna that claims that it works, for example, in this case, LTE 4G antenna on the dual band. But then you really need to read datasheet.
Mm-hmm. Mm-hmm. So in this example today, last time we were talking about Wi-Fi and Bluetooth, and today we are talking about cellular antennas.
Yeah, exactly, because it's even we will see very good effects on this of everything what I'm talking about, PCB effects, like some environment effects on the antenna, and we will also see it on the dual band antenna, right? We're on a lower frequency, and how everything affects higher frequency as well. So in this case, for a Molex antenna, we have a reference board 60 times 130 millimeters. This is specified. I took it from datasheet. They specified it, and the placement as well, they specified here. So we have our antenna in red, and then our PCB here. And you can see on these graphs, so here is this efficiency and return loss for lower frequency band. Now we are looking only for a lower frequency band, and how much efficiency change with every change of the reference board, so of the size of the PCB. So for example, even if you make it bigger or wider, it changes still. Of course, the worst case that we can see is the smallest size,
Mm-hmm.
because if you remember from our previous topic of PCB antennas, we want to have quarter lambda size of the ground plane for our antenna on the working frequency, and the lower frequency we have, the longer wavelength and the longer PCB we need to have for it to radiate good.
Mm-hmm. So before we move next, I would like to just clarify, on the board what we see, or on the picture what we see there, the chip antenna is placed on the top of the area on PCB without copper, and the yellow is the copper. And this is very important. This big area of the copper is important for this chip antenna, because that's how the chip antenna works.
Yes, exactly. So this yellow area is very important. This is a ground plane, so it's your PCB that you have, your device, the total size of your PCB, and it's very important for this antenna. So on a lower frequency especially, we last time we had an example with a 2.4 gigahertz antenna, and it worked even for that case, but in the lower in frequency you go, in this scenario it's 700 megahertz, the more you rely on ground plane size, because antenna itself is very small compared to wavelength, right? And we need a bigger ground plane in order to achieve at least some efficiency. Mm-hmm. Here you can see on the plot that blue line is what they want antenna to work. Yes, mm-hmm. So this is what they guarantee. So it goes like good 50% on for this frequency. It's okay to have 50% efficiency, and then on the higher frequency you go, you can get even 70, 60. But then, for example, for a worst case, for a smallest possible PCB that here that there is like 80-45, you can see how it drops, like 20, 30, and return loss also change. That means that even matching of the antenna, so antenna gets detuned. And because of the ground plane size.
So efficiency, I think everyone understands efficiency. It means like, I guess, how much energy goes out. But so what return loss is telling us? What does it mean?
Return loss is how good antenna matched to your input impedance. So in 50 ohm in this case, so we want the lower return loss, the better. So in this case, we go like -10, -14, and the lower the better, because it means that no reflections goes back to your feed, right, to your PCB. We want all the signal to go to antenna and then to radiate.
So basically, there's the connection between the chip and the antenna. If we have like a high quality connection, there are no reflections, so there are no losses on the way between the chip and the antenna, and everything goes out.
Yes.
That's why we would like...
If there is no losses on radiation, no losses on environment, no losses on the path, no losses on impedance mismatch or so, it will be like 100% of signal will go from your chip to your antenna.
Okay.
And and then the same scenario here, so exactly everything the same, but now we are looking into higher frequency band. Remember that antenna is multi-band, so we have lower frequency and we have high frequency, 1.7, 2.7 gigahertz in this case. And it's more forgiving for higher frequency, this ground plane size, because as I said, the wavelength is shorter, so we kind of come into good place with this PCB. And that's why you don't see such a dramatic drop. And we also start from a better point, right? We start from 90% or 80% efficiency, which is good. But even here, you can see that with a small PCB, we can get like 60% drop or so in efficiency. And antenna gets detuned as well. Return loss can be very bad.
So how is it possible that this one antenna can work on two different frequencies? Is it some kind of special antenna? What is inside of this antenna? You say PCB.
Yeah, it's just several. It's antenna, like there are a lot of multiband antennas, and PCB antennas also can be designed to be multiband. It's not a magic. You just need to have like several resonance happening in your antenna. So it's completely normal to have several. You can have even 3 band in one antenna. Of course, then it gets harder and harder to match every band to work perfectly, but then it's kind of another challenge.
So I'm just curious. So it is some kind of one wire, but it has different wiggles to have different resonances or something. I have no idea how it works.
Yeah. So in this antenna, well, I don't know what they have there inside. I mean, it's a ceramic box with some copper lines on it. But for PCB antenna, for example, you have one feed. You always have one feed because it's like one antenna, right? But then you have several, maybe some bigger chunk of copper to
so
radiate
have like
on
branches
lower.
Or something?
Yeah, branches. Yes. So bigger chunks will radiate on lower frequency, smaller chunk will radiate on higher frequency. So like this is kind of in simple words.
And they don't interfere with each other?
Yeah, I mean there is of course coupling. That's also a different thing. But usually when they are quite like separate in frequency. So for example, here we have 700 megahertz and 1.7 gigahertz. They don't so much affect each other.
Okay.
And here we have a little bit about keep out area. So all the usual cheap antennas, they require keep out area. Sometimes we have cheap antennas that will be placed on ground. For example, if you want GPS antennas up or some other cases, but most of the cheap antennas, they have omnidirectional radiation, and that means that they require no metal beneath antenna, so keep out area. And no metal beneath antenna means no metal on any layer of your PCB beneath antenna. So yeah, it's really just check really carefully datasheet when you deal with the antenna, cheap antenna, and then as well really need to be cautious about placing any metal elements like shielding, batteries, big capacitors, or some other metal elements near antenna. At least several millimeters should be between your shielding, for example, or battery. If you place battery here, should be several millimeters between antenna and your metal. So it's not in antenna like near field, and it does not disturb antenna performance. And best placement for cheap antenna, usually for this type of antennas. So when you have omnidirectional radiation pattern, and when you don't have any ground plane beneath antenna, the best placement is in the corner on the shorter side of PCB. So here we have our PCB, no metal here on the blue area, metal here on the your ground plane or on your PCB, and then we place antenna in the corner, this corner or this corner. And this considered to be the best and the most recommended from any vendors. Usually, like all vendors who do similar types of cheap antennas, they all recommend this kind of placement, because then your antenna can radiate using all the length of your PCB. And here you can see some not optimal solutions. In this case, well, antenna, we have
antenna
the same,
is placed on the edge, but there are still...
Yeah, on the edge, but on the longer side of PCB, right? Compared to here on the shorter side of PCB. So it cannot use the whole length of the PCB to radiate more efficiently. And in this case, it's just funny for me, because why would you place antenna like this?
But we have seen this.
Yeah, so... with the PCB antenna, yes, unfortunately, but I haven't seen with the cheap antenna yet. But maybe after this video, I will be surprised again and see some other. Yes.
Okay.
And talking about feed, most of the antennas that exist, the cheap antennas, they all match to 50 ohm, and they require your feed to be 50 ohm.
Mm-hmm.
So if you don't have 50 ohm feed, then you will have losses, and you will see it on your return loss, right? This graph that we looked at before, and yeah, that will just affect in more reflections in your system, and will reduce efficiency. Sometimes when you have your antenna, it's worth to have matching network. So to place several components before the antenna. So here we have feet of antenna, and we place several components in our matching network.
Mm-hmm.
It helps to tune antenna back a bit. So if we change like something, add some enclosure plastic, or we change maybe reflector or change the position, it can help, but it's not some kind of super saver.
Miracle.
Yeah, it's not a miracle. It only helps a bit, and it's very limited, and it will bring losses to systems. So that also needs to be cautious about, because every element, nothing comes with free, right? So every element has losses as well. So
I would like to point out, if someone is interested to know a little bit more about these antenna matching and all these elements and components, I have created a video on this topic, so I will attach it somewhere. You will see it, and then you can watch it. It was a really cool video.
Yeah, that's good. I mean, that's very also always good to learn more about this matching networks. It's very sometimes it helps a lot with antennas. And here we have some examples, like what can be matching network, can it look like.
Oh, you have a few things here. Yeah, okay.
Just 1 minute about that. So for simple antenna, one band, right? For example, Wi-Fi, Bluetooth, GPS, or so, we can sometimes get by without any matching network if antenna is simulated and done in good way. Then we can get by without anything. And sometimes it's like 1-2 components in matching network required. For multi-band antennas, for example, antenna that we have today, this dual band 4G antenna, bigger matching network required. Usually it's, I would say, 4 elements. Sometimes we need 5 or 4 elements, because we need to really match both bands, right? It cannot be just one band matched good and then another band suffers from that. So you really need to kind of you really need this capacity in your matching network to accommodate both bands. So now we can go to simulations, and this we will talk about a bit later. Something on the dessert. In the beginning, we have our simulation that I just showed. So antenna on the reference board. What they recommend to have, right? They recommend to have 130 here in length and 60 in width.
Can I recommend? Can I sorry, interrupt you? So where did you come up with these numbers? Do you have data sheet, or can we have a look or what they?
Oh yes, right. They here, so they have a data sheet for this antenna, and they specify reference board always for like every antenna. They have reference board, they have radiation patterns, they have everything here. And in this case, well, it's kind of long. In this case, for example, here they have 130 as reference and 60, and then yeah, they also have, like, for example, how much keep out area you need to have here.
So this is a good application note. So when someone is selecting cheap antenna, they should go with a manufacturer with good documentation.
Yes, for sure. So here, for example, they have these 2 antennas, so it's double in width because they have like a MIMO application. but we only have one antenna, so we have 130 and 60, and yeah, so here they have all the parameters. They have keep out area 12 here, and I took all this data that they have here, and I just put it into the simulation here. So I have my here I have my PCB, and I have some chip, and here this is just dielectric. This is Molex antenna that they provide. So the model they provide.
So they provide the model?
Yeah, they provide the model. You can download it and simulate. So that's very good that they provide the models. And I mean, it's quite usual now for vendors to provide models, because as you might already have a hint that it's quite tricky, right? So you cannot just place it in like on everything. You need to, like, if you have simulation software, then it's better to simulate. And yeah, so this is what they recommend to have: the placement, what they recommend, the keep out area, what they recommend, the size, what they recommend. What we have with this, we have this is our S parameters. So basically, okay, maybe we can not look in numbers or so, not to get too deep, but we have two resonances here, right? Obvious two resonances. One is happening somewhere around 700, 800, where we would expect it, right? Because this antenna should work in this frequency. And second one starts around 1.7 and goes till 2.7. So this is our second resonance for our high frequency. So this antenna behaves as we would expect.
So before we move, again, show the graph. So I would like to be sure everyone understands what this graph is telling us. So basically, this means these are the losses, or what is it?
This is this is reflection return loss. So the same as we saw before on my presentation, where I explained that the lower the better. So the less return loss we have from the system, the better.
And it means the antenna is going to radiate on these frequencies which are in these lower points.
Yes, exactly. So where we have lower points, this means that antenna resonates on that point.
Okay.
So, and we need to have two resonances in order to resonate on both frequency bands. And here we can see efficiency. So we have two frequencies. I just took one frequency from each band, 700 megahertz and 2200 megahertz. And we have 75% and 99%. Yes, 99%. This is very good. It's very easy to achieve this good efficiency on a high band. It's never a problem. I designed a lot of these, well, not cheap antennas, of course, but custom antennas for cellular, for 4G, for LTE, and it's never a problem to have good efficiency on the lower, higher band. It's always a problem to have something good with the lower band. So it's not surprising here. And of course, also pay attention that this is very, very easy setup. We don't have any enclosure, so we don't have anything around. This is just free space, so we don't have any losses here, right? Of course, it won't be the same in real life. If we want to have really accurate simulation, we need to add enclosure. We need to add all our metal batteries or something, all our flexes that we have, and then we will have more accurate simulation and maybe more realistic. But it's actually realistic to have 80-90% efficiency on that higher band, so it's not a problem.
And I'm just curious, so does it still work okay? Because this higher band is using multiple frequencies, or it's not going to use exactly the one which is in resonance, correct? I have no idea how it works actually.
What do you mean? That's
because there is a range of the frequencies, like big range.
Yeah, range of the yeah. You mean that it's kind of quite wide band?
Yeah.
I mean, in here for efficiency, I took only one point. But for example, if we looked here for this graph, here we have efficiency over all frequency bands. So 1.7, 2.7, and it's like for our blue line, that is reference, it's quite good over the whole band. So yeah, I mean, it just takes more time. That's why I don't have all these points here, but I mean, to simulate.
I asked because there is only one very small peak in the.
Yeah. That you mean. Yeah, that's why you need matching network to have its kind of broader and to have its. So basically, what we what we see here, it's raw antenna impedance without any matching network, just feed 50 ohm feed to antenna, and then what we want to see here is just that it resonates close to where we want. And then when we have our matching network, as I explained before, like 4 or 5 elements for this application, we will, with this matching network, we will try to achieve good performance over our broadband. So from 700
so you can change the peak to be a little bit wider.
Wider, yes, exactly. Not as deep, but wider. Yeah. Yes. And here we can see that how antenna, like this is the field of antennas, in ZY plane. And here you can see that this box is our antenna, but it actually also resonates using ground plane. So if you can see, the red is the peak of radiation, so and the peak of field. So here you can see that it goes and it radiates here, and if we see it on our YX plane, we can also see here that it radiates using the ground plane. That's why it's very important to have appropriate ground plane for this application. And okay, so that was reference, right? Quite good, not bad. And if we go to our smaller bands, so this one is 40 times 70. So we still, our antenna fits perfectly here, the same position as they recommend, right? And the same, maybe I need to, yeah. So clearance the same, everything the same.
But smaller ground plane.
Yeah, smaller ground plane. So what we can see here is that still resonates around where we would expect. But you can see that something happening, like it doesn't look exactly like like it used before, right? But if we just look into this, like if we just look into return loss, then I would say, okay, this is fine. We still can tune it. But if we look into efficiency now, this drops to 30%, and it used to be 70. So as I said before, if you remember, this is especially critical for lower frequency. It's not so hard to achieve good performance on a higher frequency, but on a lower frequency,
because lower frequencies they have longer length waves, so they need longer.
Yes, they need longer ground. Yes, to radiate, because we have this correlation that ground plane should be around a quarter wavelength, and if wavelength longer, then the ground plane should be longer. So this already not so good. We dropped quite a lot, more than double here. But what if we have the same board, but on the side?
I'm curious.
So here we have the same board, so 130, 60 in width, but we place our antenna on the side, and we have also good keep out area as they recommend. Like all this data is the same. If we look into return loss, we still see quite okay. So we have one resonance, second resonance. Everything is kind of good from this point of view. But then if we look at the efficiency again, we have drop, right? It's around 30 again, and here, okay, 98 from this side.
So how this efficiency is calculated?
Efficiency is basically like what total power we radiate, compared to input power to our antenna.
So it's some kind of calculation behind, and then it just gives you this number.
Yeah,
Okay.
and here this is very interesting to see compared to previous animation that we saw, because if you remember, I mentioned that we radiate with our PCB as well. It's not only antenna that radiates. So in this case, it's the same. We can see that our antenna, it doesn't use the whole length of PCB. So it tries to radiate with this ground plane, but it kind of radiates only with half of it, because it feeds from here, and then we have fields that try to radiate with the shorter side of the PCB, and doesn't radiate so efficiently as we would like. So that's why we lose more than half of our efficiency. So here you can see it radiates here on the side, so yellow, and then
so because the edge
so
is short, it means it can radiate on, and we are expecting like longer wave or something. That's why.
Yeah. So basically, like it kind of tries to radiate with this shorter edge, but then it doesn't utilize the whole length of the PCB. So field goes like this, shorter way. So that's why we don't see. And also we have a change in radiation pattern. So we didn't. If you remember from the last time, we want to have this donut, right? So this is our reference board, perfect donut shape. So donut shape means that it just radiates around antenna everywhere.
Can we show the board?
So yeah, our antenna is.
You can put 50. Put there 50, so we can also see the board a little bit.
Yeah, maybe. Yeah, sometimes, but I think 50 is too transparent. I don't know. It doesn't work logically. So okay. So here our radiation pattern on the antenna. So you can see that it radiates around antenna all around, right? And like perfect donut shape. That's called donut radiation pattern. So in our field, and if we go to the side antenna, so it has kind of donut shape, but for example, in this side, we don't have this null that is supposed to be in the center. So something sketchy happening, like already from the side of it. And then when you go here, you also can notice that the gain is negative. We don't usually want to have a negative gain. Why would we want to have negative gain, right? We want positive gain because we want to have gain in at least some direction here. But because the losses are so bad, because what is gain, right? Gain is directivity of our antenna minus losses. And losses are so bad in our 700 megahertz frequency in this antenna that we have negative gain, and we have such a low efficiency, like, well, exactly as in this small band.
So how the gain looks in the good one?
The gain here, we have like 2.5. Well, 2.5 is maybe
the red one.
Yeah, it's the red one. We have actually maximum 1.2, but I mean it's okay still for this kind of, because it's omnidirectional antenna. You don't have one peak, right, where you direct all your gain. It's omnidirectional, so gain kind of gets all over the place. So we don't expect high gain here, but at least over zero, a bit over zero. So
and the other one, I didn't know what was the maximum there.
Yeah, and the other one is I guess it was this one. Yeah, it's minus. So that's also why you should really be cautious about where you place your antenna, because you lose efficiency, you lose gain, you may have some losses, you may have some detuning happening, and so. And okay, so
I'm going to interrupt you now. So when we are talking about this, can we go back to the application node, because I think there are some graphs, and I would like to just explain. The
Parameters,
radiation
okay.
graphs, down.
Radiation graphs. Okay, yeah. Here I think they have this radiation patterns.
Oh, okay. So this is exactly what we could see in the simulation. Because I would like to talk about this a little bit, because normally people will see datasheet, and in datasheet they will see this radiation graph. So I would like to be sure everyone understand what this means.
Yeah. So here in every datasheet you would have a radiation pattern made made in simulation, as I showed now, and as well on the reference board and in the right position on what they intend this antenna to be used. And here we have as well this donut shape. Maybe well, it's 700 megahertz here, for example, and so here 800. It also depends on the, of course, of the scale what they chose for antenna. So that's why we see somewhere more green, somewhere gray, but the shape is round, right? So and our antenna is placed here where we see null. So the blue is like null, and then it radiates around itself. So that's exactly what we saw as well now in the simulation. And here it's on a higher frequency, so it becomes a bit like maybe not so round, but it's still supposed to kind of cover a round antenna. Yeah, this is very good to check and to see like what you expect. But again, this works exactly like intended, only on the reference board.
Can we also have a look? I think there are also like 2D diagrams, not 3D. So we understand also these. Yeah.
Yeah, here it's 2D. So this is basically just cuts on the like here you can see the axis of like how antenna is placed, and then you have your 3D pattern that I showed just now, and you cut it in the different slices. So X, Y, Y, Z, X, Z, and then you know how your radiation like looks in this plane.
Okay, so this is what it means. So I hope everyone now understand what these graphs mean.
Yeah. So this is also like, for example, here, XY cut, yeah, so it's kind of like round, and if we want to have our omnidirectional, we need to look into something like that gives some like semi-round shape around. So, and here we have like some nulls because it's this like XY plane when we have this null. So if we cut like through this null, then we have this like 8 shape kind of. So yeah, this is as like expected graphs for and cuts for this. You can get the same in the simulation if you have this simulation. If you don't, you just look for this in the datasheet and yeah, apply it to your application if you want to have these radiation patterns.
Okay, we can go back to the simulation.
Yeah, so but as I said, so what we look into now, this is just antenna in open space, right? We have our antenna, and nothing happening with it. It just radiates as it wants in open space. I wanted to have some like interesting case and to kind of think about what happens if we, for example, we design some device for some antenna for wearable device, and we want to place this antenna somewhere, not necessarily on the like our palm or our hand, but maybe on the body. But like human tissue is still kind of similar, and it will affect antenna a lot. So I designed a lot of antennas for wearable devices, and in these cases we always need to simulate and then test when we manufacture our prototype. After that, we test antennas always on with this environment. So on some human tissue like dummies, some special like dolls and special things that imitates human tissue, and we measure with it in the lab, and we do the same in simulation. So what do you think happens when we have human hands? So what is human body? Human body is dielectric that consists a lot from water, and water is very, very loosey dielectric. So what happens with our antenna when it's placed into very loosey environment? well, obviously it will have some unexpected losses that we kind of don't have in open space. And if we look at the S parameters, it's quite good. And that's always happens because S parameters includes losses. And if we increase losses in our system, in our environment, we also can see it in our S parameters. So it's getting like maybe deeper, some deeper dips here.
Mm-hmm.
And we can even think that, okay, maybe our antenna works perfectly because we have such a good return loss now, right? And then we look into our efficiency, and we have 10% efficiency when we placed on our on the hand, and only for the. If you remember, when we changed a lot of things with our PCB, even with small PCB, higher frequency still stayed at 98% efficiency or so, and now we 38. So even with the higher frequency, we dropped a lot. And what happens with the gain? It's not donut anymore. It's this, right? Because radiation doesn't go antenna radiates upwards because the electric is so loosey that it doesn't want to go like to the loose environment. Air is much better for radiation to go right up. So this is how it looks like. And what we see here in these colors that we have is actually SAR. So SAR is a specific absorption rate. Specific absorption rate, a bit tricky to say. That's why we say SAR. And it's basically shows what gets absorbed by human tissue. And it's very important for wearable devices to have this, and it's even certified. You cannot just release your wireless wearable device without this specific certification.
So there are some maximums for this SAR?
Yes, so there is a maximum like that you need to calculate, like per like 1 centimeter of tissue per like 1 kilo or so. So it's different for different power levels, for different like output powers, but it's very important to simulate it when you work with wearable devices, to simulate and then to measure. There are a lot of laboratories that specify in certifying devices for like mass market to have wearable devices, to have this certification, because you cannot sell your device if it does not pass this certification. So, and here we can see like how our so red is like the kind of maximum impact what goes inside our arm. So what happens is this lower frequency, so from 1 megahertz to approximately 10 gigahertz, this wavelength, it's quite good, penetrates our skin and our tissue. It goes through us and absorbs by our body quite well. But if we keep to these limits that we have, these SAR limits, then we don't cause a lot of things in our body. We don't. So what does it actually do is increase temperature inside our tissue, this radiation, right? But if we keep good limits, healthy limits, then we don't increase temperature in some like scary amounts or so that it doesn't affect us. So this is what happens. And this is also very, like, for me, it's very interesting that we can see this effect. So for this kind of application, I would never go with any cheap antenna, because wearables is very, very tricky. You really need to think about your environment. And I would totally only go with the custom antenna that's specifically made for this application.
So it would be radiating only up, for example.
Yeah, for example, yes, a lot of antennas that we want. If we want this kind of application that does not radiate inside our body, for example, we want to have like only one direction, then we can design different type of antenna, not this type of antenna that's intended to radiate around, right?
Mm-hmm.
So it cannot even itself radiate like only one direction. So we better to design antenna. For this application, it's good to have some overground antennas. So for example, we have full ground, and then on like third dimension, we have maybe like printed antenna or like 3D antenna that goes above the ground and that radiates up, not and then in this application human tissue even helps antenna even more because it's kind of plays like a more reflective area beneath antenna. So that's even so if you know what you're doing, then it's you can kind of turn every environment to be a bit helpful. But I also wanted to show a comparison about with all the cases that we looked at today. So here we have as parameters for all our cases, and the reference is the red one. So as you can see, we in every case, even the worst case with the hand when we had only 10% efficiency, we still have our resonances happening. So so in this you cannot judge antenna just by return loss. That's basically conclusion from that. You have your resonances and you still get some radiation happening on that frequencies. But then what is the quality of that radiation? What is the efficiency? That we can see here. So our reference, remember, so it was 75 and 99% in open space. And then it dropped to 30 and 97 with a smaller board. Yeah, the smallest board that we had. And then when we placed antenna on the side, it was still 30 and 98%. And then when we had our reference board, perfect placement, but in a harsh environment on a human body, we have 10 and 38%.
This is very important to point out. You still have like the best board as you could design, but you place it into wrong environment, everything is gone.
Yes, yes. That's the main point. You got it correctly.
Okay, can we go back to the graph? So the green one was on the hand? I'm just curious.
This one?
No, the graphs which you had before, the comparison graph for the
S parameters.
Yes, this one. So the green one, no, on hand is the green one is
green one is a small board. So small board, the boards from like efficiency point of view, if we compare just boards without hand, without environments like in open space, and also with the tuning, it's quite bad. I mean, we don't have any matching network here. It's different story how you would match your antenna, but I can say already now that even with some perfectly matched matching network with a good like you spent in a lab a lot of time matching this antenna with this small board, you cannot achieve the same as with the reference board with the good matching. So that's just physics here.
Okay, I understand. So these are all the examples what you have.
Yes.
Yeah, but again, this is interesting. And last time I know what was really interesting for me to find out some of these some of the environment or not doing proper design also shifted these resonances too much. So we don't really see it here.
No, we don't see it here. Yes. Well, I mean, we have some shift here, right? Like it's just not so big, maybe like 50 megahertz or something. And here we have bigger one. For example, with this green one, see how it shifted.
But so because it works on a very wide range, these shifting frequencies is not so critical as for 2.45.
Yeah, with the 2.45, we had only like one frequency, and then if we shift a bit, it's very noticeable. And in this case, we don't see such a huge shift, but still we see a lot of things happening with efficiency that's much more important than this shift, because this shift, even like with the kind of maybe you have slightly different reference board, slightly different board than the reference board, and then you have maybe slight shift, you can still return it back probably with the matching network and keep to maybe not the same efficiency that reference board showed, but still kind of good level. But yeah, if you very far away, then it's not possible to tune back with matching network.
Okay, so it also means when someone is designing a board with PCB antenna or this on-chip antenna, it's good to always include this kind of tuning components, or?
Well, yes, if it's especially if it's some dual band, some like complicated like cellular, always include matching network. For cellular, I don't even think that it's possible to have some good good efficiency to good results over wide bands without matching network. Maybe for simple, as I said, like for simple antennas, just Wi-Fi antenna, I designed a lot of Wi-Fi antenna. Well, it wasn't cheap antennas. It was custom antennas that designed specifically for this device. And then you can get by without matching network.
So you directly connect the antenna to chip and...
Yeah. Yes, exactly.
And you tune the antenna exactly for the environment.
Yeah. You tune antenna for environment, and because it's kind of higher frequency, right? 2.4, it's not so low, it's not so sensitive to like all happening around like 700 megahertz, for example. And then if you do simulation correctly, if you measure it correctly in a prototype phase, then you can get by without any matching network, and then you will have less losses in your system because matching network is loosey, and then you just have better performance overall. But sometimes even like if you want to feel safe, or if you have cheap antenna like for Wi-Fi, Bluetooth, you can put 1-2 components in a matching network, and usually all data sheets, they have approximate like schematic what elements, like what like you have parallel or like like parallel capacity, or like or so they usually put it in datasheet. And then if you have some like solder station or some VNA, you can even tune it yourself, just change some like this. If you can see that your S parameters on VNA is shifted a bit with the matching network that they offer in a datasheet, it means that your environment and your reference board is different from what they intended, and then you can change these values of these components. That's called tuning the antenna, and you can change these values and tune antenna manually with the VNA.
Okay, I would like to again point out, if someone is interested, I already made video on this topic, so you can watch it. Okay, so this is everything for today, Katerina, correct?
Yes, this is everything, yes.
Okay, so if, because our first video, it has got many views and many questions, so if someone has any questions, they can leave it in the comments. And also, if they have any tips for future topics, what people would like to learn about in this antenna world, then again, leave the tips, and
yes.
And if there is something really interesting, we can make another video next time.
Yes, true. Okay. Thank you very much.
No, thank you. Thank you very much, Katerina. And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our Fedevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments, and see you next time. Bye.